you're not expected to understand everything. It's really just going to be an introduction. I was exposed to this first when I was an undergrad, then I've been trying to understand a bunch of it ever since. It's something you can carry with you all through your life. So, I hope we can be quite agile, quite interactive, and this is a small class, so wherever you guys want to go, if there's things that are particularly interesting that you want to explore in more detail, I have a syllabus. I've got a bunch of things that we have to get through, but the way that we do it, the way we explore those topics, can really adapt to the people who are here, and the speed they want to go and the things they're interested in. I would ask everyone to have their webcams on all the time, please, like in a real class. You wouldn't show up to a normal classroom with your face covered, except in a few very specific circumstances, and it's no different in an online session. We need to see each other and we need to talk. So I've also disabled the text chat. So if you're very encouraged to chat, but please can we chat as we would in real life, verbally. And usually it's fine just to interrupt if you've got something to say, or if you want to be super polite, then you can raise your hand with the little raise hand option. Let's try and make this as much like a real classroom in Lincoln as we can. Yeah. So with that in mind, could we maybe just go around everyone? It's a small class, so we could just go around. Could everyone just talk for 30 seconds about who you are and why you are here? Why did you want to sign up for something like this? And should we go around alphabetically? We can see the participant list. It's a good way to check that everyone's cameras are working and everyone's mics are working, and to all say hello to each other.
I guess I could go first if you want.
Okay, go for it.
Yeah. Hey, my name is Elliot. I was on placement last year, so I have come back to a completely new set of computer science students. I chose logic and computation because I thought it sounded extremely interesting, and some of the things you talked about in the introduction slides and some of the extra reading you suggested did sound extremely interesting. So I thought I would give it a shot, and I did expect it to be a little bit hard, and the fact you said it's going to be hard right at the start does sound interesting, but I think it sounds up for the challenge. So
good, excellent. Anyone else?
Hi, my name's Finn. I don't own a webcam, but I will make sure that I buy one between now and next week for my desktop. I chose logic and computation again because it sounded super interesting. I just liked the sound of it, wanted to explore it a bit more. Didn't seem like a better time than now, really. So yeah, it's good.
Yeah, cool, thank you.
Hello, I'm hoping my microphone actually works. I'm David. Some of you might know me as the red guy, if you remember those shenanigans in first year. And I'm doing this module because it looked like fun more than anything. Yeah.
Cool. Thank you, David. Who else have we got?
I'm happy to go next. I don't know if you can hear me.
You're a bit quiet there, Ryan.
Oh, I still haven't. I don't think I've set my mic up. I'll come back to me. I'll just set my mic up properly.
Okay. Shall we go to someone else?
Hi, I'm happy to go next.
No, Gary. No, Gary, you go first. You're at the start.
Okay, no, thank you. So yeah, my name's Gary Clausen. I'm really excited to be here. So I felt this was sort of the third in the series from architecture TSC to logic. So it's sort of what compelled me to sort of take part in this module was the idea of mind, body, and spirit. So that sort of really sort of completed it for me. And also in the introduction, it says stated it would be hard, so I'm interested in doing something that was hard. The rest of obviously the modules are hard, but I truly believe this one would be, and so I'm interested to see how far I can extend my own thinking. So I'm really excited to do that.
Cool. Thanks, Gary.
Hey, so I'm Matt. The reason that I'm taking this module is because having done reading around it and having done other courses and such, this is what I've taken computer science to actually be, and in that sense, I think not having like really being able to explore it in depth alongside other people. Like even taking online courses on something like MIT, you don't get like the same like collaborative experience. So I thought it'd be good in terms of being in Lincoln with people that I'm familiar with, talking about things that I'm really interested in, exploring it deeper. That'd be good.
Cool, great. Thank you.
Oh, there you go. Hello, I'm currently in a void because my green screen doesn't work properly. But hello, I'm Matthew also. I chose this module because, well, I'm very unfocused in my reading. I just kind of choose whatever I want to read, and then it was a really interesting topic, and I just wanted to get a look at a deep dive into lots of reading, some of the fundamentals of this, of logic and computation. It's a really interesting field. So yeah, it's just something that really piqued my interest. So.
Okay, cool. Thank you. Anyone else?
Hello, can you hear me now?
Yeah, now we can hear you.
Yes, I'm Qing, and I'm learning the functional programming now. So I think some part of the functional programming is related to this module. So I'm trying to learn that, but find it's hard. But I like to face the challenges. So that's it.
Good, good. Yeah, functional programming would be a really nice pairing with this stuff for sure. A lot of the ideas in functional programming are taken from the underlying lambda calculus typically. Or if you want to design your own programming languages, and some of you here have worked on your own languages, then again you'll find the concepts showing up in language design. Good. Anyone else want to say hello?
Yeah, I'll try again if you can hear me better.
Yeah, hi Ryan.
Hi. Yeah, so I was on placement last year as well. So coming back sort of to just back into this uni thing. In second year for my group project, I was in a group designing a compiler. So we touched on some of this logic, and as one of the other guys said, this is what my idea of sort of computer science was before joining. So it would be sort of a shame to miss this opportunity. And yeah, it does look difficult, but it does look, yeah, like on my level. So hopefully be good fun.
Yeah, excellent. Are we done? So we still have, is it Dana? Thomas Burrows, Tommy Wilson? Maybe you guys don't have working microphones. Tell you what, I'll turn the chat back on briefly. So if you want to say my mic is not working, but we really do need to have working mics and webcams for this, like a real classroom. Okay, so yeah, let's try and make this as much like a real class as we can. A couple of you have mentioned that you want to study with other human beings and interact and try and learn together. So the plan for today, I'm going to talk for a bit. Technically, these sessions are scheduled as a 1-hour lecture followed by 2 hours of workshop. In practice, they've been timetabled all together in a big 3-hour block, so we can be somewhat flexible with that. But in theory, we'll do an hour of talking and 2 hours of workshop. So a question from David. Or
just a quick one, because I know that attendance is now being monitored for online lectures. Is that being done for this as well?
Yes, that's an excellent question. So we have access code, which I will paste into the text chat for you right now. Yeah, let's do all the admin stuff.
And will we have another code for then the quote unquote workshop period as well?
Yeah, there's a second one. I'll just post them both on here right now.
Okay.
That's the workshop code. Okay, I see. Unfortunately, I'm currently sat in a darkened room and my 1-year-old daughter is currently sleeping. This won't be a regular occurrence. Yeah, okay. We all have our environments that we're trying to work in. Fair enough. Okay. So yeah, in theory, 1 hour of talking about stuff and a couple of hours of doing things, but we might play around with that. So what I wanted to do today is give an introduction to the subject that we are calling logic and computation. From its name, you can tell this is kind of two subjects. There's logic and there's computation. These subjects are very intertwined with one another, so it makes sense to study them together. If you were doing a degree program more focused on these fields, they would often be taught as two separate subjects. You take a module on logic and a module on computation. And you can really do a whole degree in this kind of stuff, right? You'd have modules where they get applied to all kinds of topics in computer science, such as designing semantics of programming languages and type systems and verification. We only have one module, so I've really got to try and pack in as many of those ideas as I can in a very introductory way. Hopefully this is something you're probably not going to understand in one module, but you're going to get an idea of what is there. And throughout the rest of your career, if you find it interesting, it will give you a huge reservoir of interesting things to continue learning about and to apply in practice as you go. I'm still learning. I didn't understand very much of this at all as an undergrad. Now I understand a little bit more. I certainly don't understand all of it, but I think it's important to show you guys what this is and where it is, so that you can find out and explore as you go along yourself. So today I want to try and get across the idea of what is logic and what is computation. We've touched on these subjects somewhat in other modules. So for example, where have we seen theoretical logic and computation already? Can you guys shout out some modules?
Artificial intelligence, specifically a lot of classical AI deals with logic.
Yeah. So did everyone here take that module? Did everyone do prologue and first order logic?
Yeah, I think second year is mandatory, yeah.
Yeah, it's mandatory.
Yeah, I believe it's core.
Yeah. Okay, so what else have we seen in these areas so far?
Boolean logic.
Boolean logic, yeah.
Boolean algebra.
Yeah.
Would you say also some of it was in architectures with the sort of gates?
Yeah, right. So when you go to digital logic, that's a very practical hardware instantiation of logic. That's really turning the high volting theory of logic into bits of wire and making it do something useful. Okay, and yeah, you've probably heard me allude to obscure things about Turing machines and lambda calculus and Halting problems in various other places, right? These ideas come from the theory of computation, which means trying to define what computation is, and especially what are its limitations. So look, we'll talk a little more about these concepts. I'll go through the history of it. You know, in architectures, we went through the history of computing machinery. So computer science really has two histories that collide with each other in 1936. The history we've seen before is the history of machines and practical calculators and computing machinery. So what happened in 1936 was that it collided with this other strand of thinking that has its own history, the theory of algorithms and defining what is mathematically possible and impossible. So we'll try and look at how these two histories evolved and collided with each other in 1936. You know, this is important. Again, someone Ching, I think, mentioned functional programming. So you can really see how those two histories of our subject show up in the modern world. You know, when you look at a language like Haskell or ML or many other languages now are taking ideas from the functional languages. You know, we see languages like Python and C are gradually acquiring more functional concepts. You know, this style of modern programming has come from this other history. It's come from this other theoretical mathematical history. While at the same time, languages like assembly language and traditional C-like languages have come much more from that background of machinery and practical applications, you know, from the time of Babbage onwards. Okay, so when we've done history, we'll talk a little bit about a few selected topics from modern logic, which roughly means post 1931, actually. So logic's big year was in 1931, shortly before 1936, and we'll see why very shortly. And that will take us into a quick tour of some applications. You know, where does this stuff actually show up in practical computing, in careers, in very nice careers, in many cases. And then we have to talk a bit about the usual study style and assessment. I've saved that to the end, when everyone's tired. And then we'll come back and do some workshop activities. And we're going to try and put people into small groups. And you don't have to work as a team in the workshops, but it's probably helpful to at least talk to other people. You're welcome to work as a team if you like, or if you want to work by yourself, that's fine. But I'd ask everyone just to be logged on to one of those channels at least and try and interact with some other human beings if you can. Okay, does that make sense for today's plan?
Yeah, tidy.
Sounds good.
Sounds good to
okay.
Sounds good to me.
Good stuff. Let's begin then. What is logic and what is computation and how do they fit together? Okay. So logic, broadly defined, is the study of arguments. So you may have seen some of this even in a module like problem solving, right at the beginning of all of this. Traditionally, logic was considered an art subject. It was the study of human argumentation, and in particular, studying when an argument is acceptable and when there is a problem with it. So the most famous logical argument of all time comes from Aristotle, who wrote, "Socrates is a man, all men are mortal, therefore Socrates is immortal." Okay, so in philosophy, this is called a syllogism. Okay, and syll is like a syllable. Yeah, we have this morpheme syll, which kind of means, I think, a small piece of something. You know, a syllable is a small piece of a word, and a syllogism is a small piece of logic. So it's syll and then logism. Yeah, a logism is a logical argument. So a syllogism is a chunk of logical argumentation. So what's going on in this syllogism then? you can see there are two things going in, right? Socrates is a man. That's an input to the argument. All men are mortal is an input. And the line means something like therefore. So we've put in a bunch of stuff above the line, and we're going to draw a conclusion from it below the line. Okay? And for a single syllogism like this, we'll call the inputs the premises. So this argument has two premises. It's got a line, and it's got a conclusion. Okay? So, is this argument correct? Is it acceptable? Would anyone like to offer either a reason why we should believe this argument, or any arguments against it? Any problems with the argument?
I think it sounds, well, given the first two axioms, the third, like the theorem is sound. Whether or not the first two axioms are true, I think the phrase that is used is like in all universes. But otherwise, I think, like, if you look at the overlap between sets or classes, with Socrates, man being a superset of the set Socrates, which only contains Socrates, and then mortal being a superset of man, then it's obvious that Socrates should be a subset of mortal. However, if the first two axioms aren't the case, then that's not true. But otherwise, I don't think there should be any way that they should be.
Yeah. So, I mean, is there any conceivable obscure case where this might not be correct? The thing with logic is it has to be absolutely bulletproof correct. You know, you've only got to find one counter example, and you can destroy these kinds of arguments.
Well, Socrates is defined as a man, so that variable is closed, and it is for all men are mortal. So it seems pretty neat and bulletproof to me.
Okay. Anyone else? Come on, have a pop at it. Someone try and take this down.
Could it be something to do with the language, the way that the definition of men could be something which doesn't include man? Something
I was thinking that. Yeah, like all men, rather than just a man.
Okay.
All individuals in the set of man are mortal.
Yeah. Following the language argument, that's a good point. What do you define as mortal? We could say that Socrates is immortal in the sense that in the realm of ideas, he's still considered. You could take that argument, that point of view, but otherwise, I think, like in the absolute sense in those words, you would need one of the axioms to be falsified. So if there is a man that's immortal, then the set of things that are mortal is not a superset of the set of things that are man. Yeah.
Do you think?
Very good. Very good. So yeah, in normal English, mortal means what? Someone who is going to die. But yeah, do we mean physical death, or do we mean something else, like intellectual death? Yeah, Socrates' ideas certainly do seem to be immortal. You know, we're studying some of them right now, for example. And you know, sometimes this kind of language is used, especially in religions. You know, people will use figures of speech about certain things, or people being living forever or immortal, and they might have that kind of implication in mind rather than a physical mortality.
Eternal life, kingdom of heaven, for instance.
Yeah, how do you define these words? You know, if you define the kingdom of heaven as meaning cheese, and then you say the kingdom of heaven exists, then clearly that is true. But it comes down to what it is you mean by these words. Yeah. So and any word can have these kinds of problems. So here, Matthew's picked on the word mortal, and he's saying, what exactly is meant by that? So yeah, there's clearly a potential problem here, because this argument is written, in this case, in English. It would have originally been in Greek, but when we argue in human language rather than mathematics or computer languages, there's always this scope for ambiguity. Yeah. So other ways you could attack this. Well, for starters, it's sexist. You could make a gender equality argument here. Why are we even talking about men being mortal when we should be talking about humans being mortal?
What about the women and the children too?
Yeah. Does this refer only to adult males or to adult humans? Yeah,
Unless we're discussing man as a scientific term, which is the suffix of human, in which point it doesn't represent gender at all.
Yeah. Okay. And the second premise, all men are mortal. Is that absolutely, completely true forever? There are scientists in the world now who are fairly seriously working on how to disable the aging process in cells. They can extend the lives of some animals by several years, and it's conceivable, at least, that one day we might be able to turn off human aging and produce a man who is not mortal through that process.
I'm just going on the more less computer sciencey route. That is a terrible idea. Just making people immortal is a stupid idea, because we are mortal at the moment. We will die, and we are still having a massive overpopulation problem. If we then make it so people don't die.
So there are serious. I met the guy once who runs there's a facility in the desert in Arizona where they can cut your head off and put it in a freezer for 1,000 years until we figure out how to cure death, and then they're going to bring you back again. These things do exist and are being discussed. Yeah, maybe they're not a great idea.
The weirdest thing is you need to share a freezer. Quite often they pack 3 or 4 people into the same freezers, and it's a lot cheaper to get just your head done.
You can get your whole body. You can get your whole body put in an individual one, but it's a lot more.
It's real expensive. Yeah.
Most people just do hair.
I just think that anyone doing that has clearly lost their mind, quite literally in some cases.
Quite possibly Marvin Minsky is in the freezer now. The great AI pioneer is believed to have been part of all of that.
That would be fitting, wouldn't it? Hooking his brain up to a computer so he becomes the AI.
So look, again, there's an interesting question about this style of argument. This structure is called the syllogism, and it is more generally it is of the form X is a Y, all Y are P, therefore X is P. Yeah. And the question that this illustrates is, what exactly do we mean by all on the second premise? Do we mean all men who are currently around, or all conceivable men who could ever exist in the future who we've never actually seen and have no idea about? Yeah, how can we make any sort of claim about all of something if they don't even exist yet? So we've seen. You can argue about the meaning of mortal, you can argue about the meaning of man, and you can argue about the meaning of all. Yeah. At what point does one stop being a man? Yeah. What about a dead man? Absolutely. Is a dead man still mortal, or is mortal a property of someone who's alive and is going to be dead? Good. So look, we can generally, when you're given an argument like this, you can attack it in a couple of different ways. Then you can attack the meaning of the terms within the premises. You could attack the premises themselves. You could say, is this premise actually true? If we said Socrates is a cheese, all cheeses are mortal, therefore Socrates is mortal. That argument would still work logically, but it would be based on a premise that is false, because Socrates isn't a cheese. Unless you want to go off and define the word cheese as meaning something crazy to actually make it work. So there's a difference between an argument being okay structurally from it being okay semantically. And we'll call the argument valid if it's structurally okay. And we'll call it sound if it's both structurally okay and the premises are okay. Now, when we make these arguments in computer science, we normally write them this way around rather than this way. Okay, in philosophy, they stack their premises, so it looks kind of like an arithmetic sum. When we do this more formally, and yeah, we're not going to use English, we're going to use symbols in most computer science. So this is a completely equivalent notation. We're simply going to write the premises side by side along the line, and then draw the conclusion underneath. Okay. Now, does that make sense? This confused the hell out of me for a very long time, because when you read the computer science literature, they don't usually make this connection back to the philosophical logic that it's actually based on. Okay.
It always reads left through right, Charles.
Sorry?
Does it always read left through right?
Left to right. So yeah, there isn't really left or right here. They're just two input premises. So the Socrates one and the all men one, the Socrates isn't more important. It's not first. There's just two inputs. It's like a logic gate. There's two inputs and there's one output. Yeah.
So is the line kind of like a if-then kind of thing?
Yeah, it's almost like,
you know, that sideways U in propositional.
No, don't get into symbols for implication yet. When we study logic, we are going to have to make an enormous distinction between these things. There are syntactic structures. For example, in Boolean logic, okay? In Boolean logic, there's this little arrow symbol, like A, right arrow, B, yeah? And that's sometimes read as if A, then B.
Yep.
And if any of you can remember back to computer architectures, we discussed how there might be some problems around that definition. And we'll probably go into that in a lot more detail later on. That little arrow is a symbol that is used inside the logic. So in these examples, the symbols are all written in English. We're using English words here. When you're given a logic, it consists of a bunch of symbols, and the logic is going to manipulate those symbols. And that little arrow is a symbol inside the language that is being reasoned about. That is a completely different thing from these lines here, because these lines show what we are doing with the logic. Okay, so later on we're going to see some of these premises. For example, we're going to see some of those premises what might contain that little arrow symbol. But when you're manipulating logical symbols, you don't care so much about what they mean. You're just going to follow the rules of logic. And when you draw a line, that's something that you are doing to actually make an argument.
Cool. Yep.
Now, that almost certainly doesn't make sense. Hopefully it will as we progress. There's going to be a really big theme in all of this about that distinction. Okay, the arrow is something that exists in the syntax of the logic, and the line is something to do with its semantics. The line is something that we do as a human user of the logic. Okay, or if you build these systems on computers, the line is something that a computer could do to actually process things written in the logic. Okay.
at the core of what.
Yeah, you have to be really, really suspicious of these symbols that look like arrows and implications all the way through them.
Can't we say something along the lines of, well, that's just one particular Gödelian encoding of that symbol?
So, yeah, lots to talk about. Yeah, let's save that till we get there, I think. Good, but yeah, it's good to be aware of it right from the start. Okay, so look, in this slide we talked about a single syllogism, right? A syllogism, otherwise known as a rule, is one little unit of logic. Yeah, a syllogism is like a syllable. Yeah, a syllable is part of a word. A syllogism is part of an argument. So, to make a real argument, you have to put lots of syllogisms together to actually infer something. And when we do that, it can look like this. We've stacked up a whole bunch of syllogisms together, and we call this a proof. Okay, a proof is a bunch of these rules put together in some sequence that takes you from the inputs to the outputs. And when we're talking about proofs, we will call the top level inputs axioms. Okay, so remember a premise is anything going into a syllogism. Okay, an axiom is a top level premise that hasn't come from anywhere else. So for example, here, Plato will be sad. Okay, Plato will be sad is a premise of this syllogism that is used to get us to this conclusion. But it's not an axiom because we've deduced it from all the stuff above it. Whereas Socrates is a man is an axiom because that's an input to the entire proof. Okay?
So does Plato will be sad exist as a theorem and as the input, forgotten the word, because it's kind of sandwiched in the middle?
Okay, yeah. So when you conclude something at any stage in these proofs, we're going to call that a theorem. Okay. Yeah. So yeah, Plato will be sad. Actually, where have I got that from? Have I brought that in as an axiom? Okay, let's take a look at this particular proof. Okay. So look, this is the syllogism we saw before, right? All men are mortal. Socrates is a man. Socrates is mortal. Yeah, that's the classic one. And then we're going to say all mortals will die. That's kind of a definition of mortal. Yeah. So then we have another syllogism. All mortals will die. Socrates is mortal. Therefore, Socrates will die. Okay. So actually, yeah, this is what is this? This is an English language argument. So there's always some other assumptions sitting around.
It seems to be a one-to-one truth that we know already, is that if Socrates will die, Plato will be sad.
Yeah, okay. You probably want to write an extra premise for this.
It needs an extra.
Yeah. If Socrates dies, Plato will be sad. Yeah.
Because Plato and Socrates are friends.
Yeah. So Socrates was Plato's teacher, right?
Yeah.
He was the original academic. A hand up from David.
Yeah, sorry, with all of this discussion like Socrates and Plato, I just remembered a really dumb example of I think Plato's logic being destroyed, where he apparently gave a definition of humans as featherless bipeds, and so Diogenes responded by going into his next lecture with a plucked chicken and placed it on the table and said, "I present to you a man." I just remembered that one. I thought I'd share it.
That's the kind of thing that might actually work at the University of Lincoln, right? We like our definitions here, and if the CRG says you've got to present a man as part of your artifact, and you bring a legged chicken, then they'll probably take the CRG off for you. So yeah, okay. When you make these arguments in English, you are really assuming some kind of background knowledge as well that is getting used in some of these steps. So in this case, we've kind of assumed that you already know that if Socrates dies, then Plato will be sad. But you could write it down and make it explicit here if you want. So now you have obtained Plato will be sad as a theorem as well. Yeah? So the theorems we've created now are Socrates is mortal, Socrates will die, Plato will be sad. And again, the same pattern here. You might want to make this more explicit, that if Plato is sad, then he takes it out on the world by writing really hard to read text. Okay, I've just written that in English. If Plato is sad, then his text is going to get worse and hard to read because he's having a bad day. And so again, you can take the theorem from there. You can take the conclusion and plug it into another sequence or a rule down here. Sometimes we call these sequence or syllogisms or rules, all basically the same thing. Because logic is studied by many different subjects, they all attach different names to the same things, just to confuse you. So here we've just run out of space on the page, so we could have carried on growing this argument all as part of one figure, but I've decided just to create a new one. I've taken the theorem from there, put it in as a premise here, and made my new argument down here. Okay. So was that another hand from David?
Oh no, whilst just after I'd said that story, my browser decided to crash. So yeah, sorry about that.
I had a friend at Oxford who was obsessed with this kind of thing, and he was trying to find a way to take a book out of the library. So you have to promise in Latin that you'll never steal a book from the library in Oxford, and they can never leave the library, which is really annoying, because he really wanted to take a bunch of books back to his room. And he was trying to come up with all these ways of circumventing the university regulations. And he came up with this idea that the university could redefine what the library is, and eventually redefine the entire city as constituting the library of the university. And that would be a way for everyone then to be able to take their books back to their room. So this is a real problem, right? When we see applications of logic in AI and language processing in particular, humans do a lot of work that they're not really conscious of when they define the meanings of words. And if two people don't agree on the meaning of a word, you can make the most beautiful logical argument in the world out of it, but those people still aren't going to agree on the argument, because if one person thinks mortal refers only to physical death and the other thinks it's the longevity of ideas, then those people are still going to disagree. Okay, so we now have axioms, we have rules, we have theorems or conclusions, and we have this notation to show how you can build an argument out of these components. And this is useful in everyday English. In the workshop, I'm going to ask you to try and map out an argument of your choice like this. And you might, for example, get a bunch of Republicans and Democrats to sit down with one another and map out the arguments they're trying to make. And they're not going to agree on anything, but at least you can see what it is they actually disagree on. You can try and isolate where inside an argument the problem is occurring. So if we were arguing about this question of mortality, we could have gone through this whole inference about mortality up to me being sad for having to read Plato's indecipherable, sad written text. We could go through this whole thing, and then we might isolate that it comes down to the fact that we disagreed over what is the definition of mortality. And that's not necessarily going to help us to completely agree, but at least we'll have made some progress, seeing that we accept parts of it and that we maybe both have some work to do to try and understand our concepts of mortality together. Okay, so that's logic. Let's look at the other side of this, which is computation. So what is computation? Anyone want to try? Actually, you can try even if you can see the slide, because the slide doesn't really tell you. Slide tells you what a computer is under Church's definition. What is computation?
I'm not sure. Could you say that computation is something about the composability of abstractions and of dealing with complexity?
The composability of abstractions. That sounds plausible. You're going to have to define what all of those other words mean, though.
Right.
What is an abstraction and what is composability?
So an abstraction would be, if I have something of a given complexity, I would be able to group or reduce the amount of referring to lots of different naggly bits by abstracting them all away. And then in terms of composing things, because I've now abstracted things into things which share similar properties, I now have a language with which to combine those ideas in new ways. Is a bit of a clunky.
A lot of what we seem to do on a daily basis in computer science is that, isn't it? We take hierarchies of things and we combine them together, and then we package them up in another thing, and we pass that on for the next person to use. Yeah.
Computation is taking in one or multiple inputs and producing one or multiple outputs based on those inputs.
Okay. So isn't everything computation then?
Yep.
Yeah, baking cake.
Your brain is a computer, your body is a computer, the world is a computer, the universe is a computer, everything's a computer now.
So, this is a valid position, right? This is called pan-computationalism, is a view that everything is a computer. Any physical system is taking inputs and doing something and creating an output.
I mean, if we're going on the definition of computers, a computer is something which computes. And so, then you have to define what. So, for instance, back. I remember, it might have been in one of the computer architectures lectures, I can't remember, of basically a big office room in which you had a bunch of women just sitting at desks, like with pieces of paper, and that was a computer.
Yeah. So computer used to be a human job title, right? You could just apply for a job as a computer and go and sit at one of those desks and perform algorithms all day with a pen. Yeah. Actually, the job title was for an individual worker, right? But you might think of the computer more today as the whole room full of those people working together. So we've seen for physical devices, we've seen a computer is a device that can simulate the workings of any other device, as long as you give it as much memory as it asks for, which you notice is a fairly tame way of defining infinity, right? Sometimes this is given as a device that can simulate any other device given an infinite amount of memory. Now that sounds really scary, right? That sounds like something you can never actually build, even approximately. Imagine trying to create an infinite amount of memory. You'd need the whole universe and more full of memory. Whereas if you define it as giving it just as much memory as it asks for, that's much more tractable in practice. That just means when it runs out of hard disks, it can pop up an error message and say, please go and buy me one more hard disk at a time. And as long as you have the ability to do that gradually, in theory, you could go on buying more and more hard disks, but throughout that process, there's only ever a finite amount of memory at any one particular time. So this came from Church in 1936, often wrongly attributed to Turing, who did it later in 1936. So there have been various mathematical abstractions of such machines that were proposed. So Church did it originally by proposing what is called lambda calculus that we will look at very soon. Turing did it by proposing the Turing machine. And again, back in architecture, we saw really any computing device can simulate any other, because that's what a computing device is. So even something like an abacus, if you interpret what an abacus is doing in a certain way, if you interpret the state of an abacus as representing the state of your favorite modern machine, Nintendo Switch, whatever, you probably need quite a lot of abacuses or a long time to do that. Even a simple device like an abacus or even some rocks in the sand have the ability to simulate those other machines, in theory. So computation is not quite the same thing as a computer, though. And Dijkstra, the great computer scientist Dijkstra, has this famous quote that computer science is no more about computers than astronomy is about telescopes. This is the quote I always pull out here in Lincoln when we're discussing whether to create a new module about computer science or to create one about computers. You know, computer science isn't about making your Microsoft Windows machine do database things. It's about computation itself. At Oxford, the degree is called computation rather than computer science, to emphasize that. So we'll talk more about this today. Roughly, computation has come from this other intellectual history of people trying to think about algorithms. An algorithm is a process, an abstract, deterministic process that anything or anyone can execute. Really, computation has come from people thinking about algorithms and asking questions like, what are the limitations of algorithms? Are there problems that no algorithm can solve? So computation is much more associated with the abstract idea of an algorithm rather than a physical computer. What are the limits to giving people a set of instructions or a set of rules and trying to define stuff deterministically? It doesn't really matter what particular machine you're using to carry out those instructions. The algorithm is the spirit of what the software is implementing, and then the hardware implements the software. You know, these definitions, any definition is made out of words that lead you to other definitions, and it's easy to end up going around in circles. But there's a big weasel word here in Church's thesis called simulate. Okay, a computer is any device that can simulate another device. Yeah, so now you have to go and ask, what is simulation? What does it mean for your abacus to simulate a Nintendo Switch, for example? So, you know, you could imagine setting up your abacus in such a way that you have a mapping from its state to the state of the Nintendo Switch, and when you go and look at that abacus, in your head, it is representing what the Nintendo Switch is doing. Okay, but if anyone else comes along and takes a look at that abacus, they just have absolutely no idea what it's doing. And you know, this is the idea that Douglas Adams plays on in The Hitchhiker's Guide to the Galaxy. He has this running gag that the Earth was designed as a great big computer, but no one can remember what is the representation system. So nobody knows what is being computed anymore by the state of the Earth. So, you know, we can define simulation in terms of representation. That's easy to do. We're going to use our abacus to represent the state of a Nintendo Switch. Now you have to worry about what is representation, and that's where it gets really hard. there are questions about whether you need a human in the loop at this point. Is the representation something that only exists in your head, or is it something that can be defined objectively? And when we look at logic as a formal system, from the mathematical flavor of logic, we try to really nail this down. We have what is called model theory, where you define one formal system as a model of another one. And then you can very clearly and unambiguously say exactly what representation is. You can say there's a mapping between the state of this system and another system. You still have the problem of defining what the first system was doing, but you've moved the problem away. So typically this is going to come up when we talk about syntax and semantics again. Let's say we have a bunch of symbols like numbers, and I mean the symbolic numerals, the squiggly line that you write for a number 3 or a number 5. And there's a sense that those symbols have to represent the underlying numbers. Now you have to go off and define what a number is. Informally, the number 3 is the collection of think of it as the collection of all collections of things that have 3 elements in them. Okay, so here are 3 cups, here are 3 pens, here are 3 cars. Consider the set of all of those sets, and the number 3 is what they all have in common with one another. So if you can set that up mathematically, you can then go off and define this little squiggly symbol on a piece of paper or on a computing device as a representation by saying we're going to map this symbol to that well-defined mathematical set. Okay. So representation can be of objects in the world, or it can be of other machines. That's the number 3. Numbers are especially difficult to capture, and a lot of the history of logic is all tied up with mathematics when it didn't really need to be. The strand of logic that leads us to AI doesn't think very much about numbers. It thinks more about chairs and tables and boxes and coffee cups. And in those kinds of logics, you have a symbol that looks like the letters BOX, and that symbol is representing a box in the world. It's representing an actual lump of cardboard somewhere in a room. And again, you always have this question of how does that representation work? What is connecting that symbol to the piece of cardboard? Question from David.
Sorry, it's regarding the attendance stuff again, because I've now not got the code because it crashed and cleared the chat for me. Cheers.
There's a lecture code. There's a workshop code. Okay.
Thank you.
So representation then comes in several flavors, right? We can talk about what does it mean for a symbol to represent an object, a physical object. How does this pattern of zeros and ones in your computer represent a lump of cardboard sitting on a table somewhere? You can talk about it in terms of numbers, and mathematical logic obviously is very interested in this. What does it mean for a symbol to represent the number 3? And then in computation theory, you have to then think about what does it mean for a symbol to represent another machine, or for one computing device to represent another computing device. And the history of this is all tied up with questions like, are there things that a computer can't do, or are there problems which are uncomputable? Yeah. So we're not talking about problems that a particular computer can't solve. We're talking about problems that are, in principle, unsolvable by any algorithmic method. You can always find a problem that a particular computer can't solve if you just ask it something that requires another unit of memory beyond what it's got. But remember, a theoretical computer has as much memory as it asks for. So then you're into the world of more abstract computation. And if it turns out there are things that no computer can do, is this going to be a problem? So does anyone know of cases where this might occur, or where it might really be a problem?
So there's the obvious answer, because we're going to be doing all about Turing and Church and Gödel. Something actually I was thinking about, even if we define a computer as something where if you give as much memory answers, it can do this. How does that interact with NP hard and the things that are in NP hard that aren't in NP?
So the hard
I'm not sure if that would count as something that a computer can or can't do under that definition of computer, because it's unclear if it's an algorithmic. Well, it is an algorithmic problem.
So the problems in NP hard, they are solvable, but they just take a really long time.
Yeah.
So in computation theory, we're a level above that. We don't care how long it takes in computation theory. We just want to know whether a problem is in principle solvable or not. So
yeah, of course, because you know the set of all sets that are basically infinite, and then combining and composing them, and that would be okay. Thank you.
Okay. So yeah, you can play the same kind of games here that they play in complexity theory. In complexity theory, they'll have shown you how you reduce one problem to another. Yeah, so you show that the traveling salesperson problem is unsolvable, is NP hard, and then you're going to take another satisfiability problem and show that there's a mapping between that to the traveling salesperson problem, and therefore that both problems are NP hard. So you can play the same kind of games here, but now we're a level above. If you find one problem that is uncomputable, you can then go around and show that other problems reduce to it, and therefore that they are also uncomputable. Okay, so there certainly are real cases of this. So the most notorious one is that it's an uncomputable problem to prove whether two numbers are equal to each other in the general case. If you define real numbers in any sensible way, real numbers are very strange beasts indeed. And if we have time in the module, we'll look at how Turing did this. Turing created a new way of defining the real numbers as little computer programs. And to show if two numbers are equal, you then have to show whether two of Turing's little programs have the same result or not. So now you're talking about whether two programs are equal to each other. And of course, if you could do that, you could then do a whole load of very clever computer science. You could create perfect optimizing compilers, for example, because you could look at the program that the user has entered, and you could say, go and find me a list of all the other programs that are the same as this one, or which compute the same thing. And then you find the one that runs in the shortest time, and you replace the user's program with the best running one. Yeah, so that would be a lovely tool, right? You'd all love to have that in your Microsoft Visual Studio, whatever, to click on a little button and say, optimize my code. But that's an uncomputable problem. You can't create an algorithm to do that every time perfectly. Question from Matthew.
Does the halting problem fall within this as well?
Yeah, right. So the halting problem is an uncomputable problem. That's getting a machine to predict the behavior of a program on another machine in general. Yeah. So again, you'd love to have this in your Visual Studio, right? You'd love to have a tool where you click on an icon and it says, will my program ever crash and go into the blue screen of death in an infinite loop? Yeah. Will my program ever get stuck in an infinite while loop? And clipping the paperclip could pop up and point out where your infinite loop is going to occur and help you to fix it. And again, you can't do that. That's an uncomputable problem in the general case. And the reason that this was one of the first uncomputable problems to be discovered. The reason you can't do it is because you can create versions of the task where a machine ends up trying to predict its own future behavior. Okay, if I give you a task like, I'm going to give you a question: what will you be doing at 9 o'clock tomorrow morning? Yeah, and you might tell me I'll be making a cup of coffee or something, and then I'm going to come up with a program for you to run, something like if tomorrow morning at 9 o'clock I'm going to be making a cup of coffee, then do not make a cup of coffee at 9 o'clock tomorrow morning. Okay, I'm going to give you that as your program. I'm going to say step 1, predict what I'm going to be doing at 9 o'clock tomorrow morning, and then step 2, when it actually gets to that time, if that's what I'm doing, then don't do it. So you have a logical contradiction. So that halting problem is often what is used as the target of all these other problems. When it's like the traveling salesperson problem. You're going to try and reduce these other problems, like the equality of two numbers, to versions of halting problem. So good. This puts fundamental limitations on what computation can do. Then in the areas of mathematics, we'll find there are mathematical questions that can be asked that are just unsolvable. There are tasks you can try and give an AI device that are unsolvable. And most pragmatically, it's all these issues around language design and compiler design. There are many uncomputable problems. So sometimes this is viewed in a very positive light. It's called the full employment theorem for compiler writers. It means there will always be more work for human compiler writers to do because their job cannot be entirely automated away. So that's logic, that's computation. Why do we want to study them together in a module called Logic and Computation? These subjects are inherently intertwined in multiple ways. They've evolved together over time, and we tend to use them together. So, for example, you can use logic as a model of computation. When we discuss computation in the abstract, we don't want to be talking about individual CPUs and wires and registers. We want to be talking about the idea of computation. And so various people have developed these simple models of computing devices, such as the Turing machine and the lambda calculus. There are ways of setting up what you mean by computation using logic. And this, arguably, before 1936, there was 1931, which was Gödel's theorem. And when Gödel was doing with this, he didn't think about computers at all. He was purely using mathematics and logic. But his definition of these systems, which is based on, as someone said, based on hierarchies. You take a bunch of simple mathematical functions and you wrap them up to make more and more complex functions. So those are called primitive recursive functions. So it was later understood that what Gödel had actually done was create a model of computation. So if you really want to argue this, you can go back even before Church and say it was actually Gödel who did it all, without even realizing it. That's one way you can use logic to talk about what computation is and to reason about it. You will often find logic being used to reason about particular pieces of software, particular pieces of hardware. So, for example, can you use logic to prove that your program actually works? Okay, when you've studied software engineering, you will see these systems like unit tests, where you just try out a fairly random bunch of test cases and they work, and you kind of hope that therefore your program worked on all the other inputs that you didn't test. But if you use logic, you can try to actually prove that your program will always work, no matter what. Similar for hardware, there are cases like the Intel floating point bug in the Pentium, where billions of dollars were lost because of an error in the digital logic circuit. And we now have ways to use logic to make those proofs to prove that your adder actually is an adder and will always do what it's supposed to be doing, subject to the usual academic hedgings and restrictions. To make these proofs work, you still have to assume something. You have to assume that the proof system you are using is all bug-free, and the rules of logic you're using are bug-free, and so on. So you can kind of pass the buck around. But this is still very helpful in practice, especially if you're making safety-critical systems. It's really worth doing this if you're writing software that runs a nuclear reactor, and you have to be absolutely sure that it's going to do what you want it to do. You will find logic showing up in language design. So for those of you who've been working on compilers, you have probably noticed by now that syntax is very well understood in compiler design. And it's so well understood now that you can pretty much write down the symbols for your language in something called BNF form, and then run automated tools that will turn the description of your language into a part of a compiler. So these are tools like Flex and Bison that I know some of you have been using. Now, you will then find those tools will give you an outline compiler. They'll give you your own C code that will parse the language, but you then have the problem of actually implementing what your language does. And at that point, you're in a much worse position where you're kind of making stuff up as you go along. And there are ideas, still not fully developed, but there are ideas about the semantics of programming languages where we would like to have something that is like that BNF description of syntax, but we'd like to have it for the semantics of the language so that you could write down exactly what your language is supposed to do and then plug that description into a compiler to have it generate the language for you. So there are a very small number of cases where this has been done, like ML is a famous language for having done this properly. You'll see this stuff show up in types as well. If we have time to look at type theory, there's a whole load of logical inferences involved in figuring out the types of stuff. So if any of you are writing C or C++, C++ now has this new auto type where it has to figure out the correct types of your variables for you. And this is actually a really old idea, again coming from ML. Like we said, these functional language concepts are flowing into all the other languages now, finally. So roughly what you have in those systems is a small AI module that is using logical inference to figure out the types of all your variables automatically and to make sure that they're okay, and to create compiler errors or runtime errors if there's a problem with the types of thing. And then finally in AI, the AI means different things to different people. From this point of view, we're talking about logical AI, otherwise known as good old-fashioned AI. So we're not talking about probabilities and Bayes and machine learning. We're talking about symbolic, logical, not just Prolog, but Prolog-style systems. And again, sometimes those systems are used themselves as models of computation. You can ask questions about an AI system that are intended to be questions about computation in general. Is it possible for an AI system to solve any problem or to predict its own behavior? So we'll see these two subjects are just inherently intertwined. In some places you would study them separately. If we had more time, we'd have a logic module and a computation module. But we're really just going to try and race through as much stuff as we can and see the basic ideas and roughly how everything links together. Shall we go and have a cup of tea?
Sounds good to me.
Sounds great, yeah.
Sounds
No
brilliant.
Okay,
I'll
just finished
see
my
you
copy.
guys in 10 minutes or so, I guess.
let's come back in 10 minutes,
Hell
yeah, which is 15, 20, call it 15:30. Let's come back at 3:30.
Okay.
Yo.
Super. Ciao.
Okay, everybody back?
Back.
What kind of mood is everyone in? Would you like more of me talking, or would you like to go and do something?
I'm in things as they are, but so I wouldn't say no to doing some hands-on stuff as well. Both sound good. They're both good options.
Anyone have any strong opinions? Okay, well, I'll talk for a bit more, and then we'll try and do something in about half an hour or so. Okay.
I have a question before we start. So you're talking about one of the interesting things we were doing, verifiability proofs, reasoning about programs. Obviously brought up the CPU hardware stuff, and you had the counter example from ARM, where they use ML to do verification for that because it's a non-lazy but has all of that beautiful, expression hood. However, that has a question there because I've looked at slides, and at the stuff we're going to be doing, I imagine there's going to be a lot of writing programs to generate proofs about formal systems and such. In terms of using particular languages and stuff, we're going to be using some kind of Haskell, ML, perhaps Lisp. Is that going to be something we should start focusing on, making sure we're not like, what would you say?
Okay, maybe this is a good time to talk about. I can talk about all this study style and assessment stuff, which probably gives an answer to it. I think if I show you what the assessments are going to be, that's probably a good way to answer that. So let me.
I just. Are you moving on to your section, or can I ask what you want to ask a question now?
I'm just going to jump to the stuff about the assessment and study style. One moment. So ultimately, this module is defined by its assessments, like all modules. There are two assessments. One is a portfolio, which is 60%, and the other one is an exam. Or this year, it's a time-constrained assessment, TCA, which is 40% to cover the theory. So let me show you what you actually need to do for these assessments. Here we go. The assessment is sitting on Blackboard now, and it has, so the portfolio is on Blackboard right now, and it has two components. Now, according to the wording of the assessment, it doesn't matter what languages you use, right? You just have to demonstrate that you can do these things, and they are deliberately quite open-ended and vague, again, because this is a new module. Okay. So we're probably going to do the lambda calculus first. Okay. What I'd really like you guys to do, if you're good enough, is build your own lambda calculus interpreter. Okay. This is effectively building a small compiler. So if you're going to work at that level, it's really up to you what language you want to do this in. You might like to use a functional language, or you could do it in C or whatever. Note though, the wording of this question is deliberately open-ended. You don't actually have to go and build your own. You ultimately only have to describe the design of it. So if you don't want to build your own, I can give you guys I think a Python version of this to have a look at. I can show you one that someone's already built. You can go and describe the design of that, or you could just describe it from a purely theoretical basis. I wanted to make some exercises as part of this where you will program in Lambda calculus. So the Lambda calculus will be your programming languages. Effectively, it's a very simple functional programming language in itself. Okay. Then for the other task, we are going to use logic to model and solve a problem either in AI or verification. So this could be a kind of blocks world AI thing, or it could be proving a piece of hardware or a piece of software. Again, depending on where you guys want to go, really, we could look at specific packages that do this. You know, that there are languages and systems for doing verification. Or we might look at it in a more theoretical way. You know, you could do this with a pen and paper. I think we really want this to evolve with this collection of students and just see what we're most interested in. Yeah. So yeah, to answer your question, you don't need to learn a functional programming language to do any of this, but it might help because there's a lot of concepts that are shared between them. Does that make sense?
Yeah, that's super.
Yeah.
Obviously, writing a Lambda calculus interpreter is a lot of fun.
It's your classic. Every computer scientist should write a Lambda calculus interpreter. You know, I don't think you're a proper computer scientist until you've done that. It's just
it's possible future work. I've done it before, but I really want to do it with laziness. I've never made a lazy language before. I'm really okay. Yeah.
Right. So it sounds like we're going to have fun. While we're here, let's take a look at the other part of the assessment, which is the exam. Note the portfolio is the larger part. The exam, I think, is going to have 3 questions, and they will cover roughly these kinds of topics. So these are learning outcomes or something. So roughly, there's going to be something about different models of computation. That means Lambda calculus, Turing machine, maybe others. There's going to be something about how logic and computation are linked, like I was just talking about, and there'll probably be something about the limitations. You know, a lot of this theory is about what cannot be done with logic and computation. Okay.
Will these be essay-style questions?
Everything is designed to be quite open-ended. So, yeah, I'll put in questions that. What am I allowed to say?
Well, it basically be up to us to show understanding however we can.
Yeah, you've got to show that you understand these things. So yeah. I will probably, I'm not just going to say how is logic used in computation, because you could just prepare a canned answer to that. So probably for each of these things, I will pick a question that contextualizes it in some specific way, just so that you have to think a bit on the day. So yeah, probably your answer will be a mixture of written English and some equations.
Cool.
If you want to use your skills to show off actually setting up a problem and solving it using logic, go and do that. Or if you prefer to write in English about the concepts, you should have the ability to do that as well. I mean, these subjects are hard, and we're not trying to turn you into full-on logicians here. We're just trying to give you a basic understanding. So in some cases, it's easier for everyone if you just write in English to show you have a basic understanding. Okay.
Yeah, thank you.
Good. Right, let me go back. How much of this shall we do? Let's do some of the history today. Again, it's a new module, so we really have no idea how long different slides and things will take. So we're going to have to be agile throughout all of this. And also Blackboard has just crashed, so it won't let me skip between my slides in any way other than clicking on it time like this. On the upside, you get a little preview of all the slides backwards this way.
I did have just a question about one of your slides on computation before. When you said you put the definition of simulation as using one machine to represent another machine, and then you talked about representation. But is using one machine to represent another machine still the definition of simulation? And then the objects in the world are defined as another machine? Or is the objects in the world and machines two separate concepts?
I don't think anyone fully agrees on this stuff, right? There are still academics writing journal articles in journals like Minds and Machines where they argue about this. People propose definitions of this. I think from my personal opinion, not necessarily that of anyone else, I think simulation seems like a relatively simple concept to me, because you can just pass the book on to representation, but then everyone agrees that representation is hard. Yeah, there are philosophers who spend their entire career trying to define what representation actually is, and still don't get anywhere with it. When we look at the mathematical forms of this, it's much easier. So I mentioned this idea of model theory earlier. So in model theory, you really are going to nail this down in those mathematical cases, because you can give a formal definition of one system and then give a formal definition of the other system, and then show that there is a mathematical mapping from one to the other, and it's all very, very clear cut. The problem with that is that you can only use one formal system to represent another formal system, rather than representing a physical object in the real world or representing another computer. So you're kind of pushing the problem back from one formal system onto another. Yeah, it's complicated.
No, that does help a bit there. Thank you.
Yeah, good. There's a lot of questions in this subject that are still not answered, and part of the fun of the subject is that some of these questions are not answerable. We're studying questions whose existence of an answer itself is up for debate. So, I might occasionally give you guys exercises that just don't have a solution, just to try and give you a flavor of what it's like, because you often don't know whether something is solvable or not. So, that's what real research is like. You don't know in advance if a problem even has a solution or how to attack it.
It's
Okay,
very fun,
so look.
yet stressful.
Sorry?
It's fun yet stressful, as I'm finding with my open-ended research project at the moment that I'm doing for my project.
Albert Einstein, I think, once said, if we knew what we're doing, it wouldn't be research, would it?
That's very true.
Wise guy, yeah. Okay, look, I wanted to talk a bit more about the history of these subjects today. How logic developed from being an art subject into whatever it is now. This goes way back. There was Socrates was arguably the original academic who used to wander around the streets of Athens arguing with anyone who he could find about the definitions of things. And then there was his student Plato, who took over, and then there was Aristotle who came after that. And Aristotle was, for over 1,000 years, just referred to as the philosopher, as if he was the only one, because he wrote so much stuff and it was so good and so definitive that all through the Dark Ages and the Middle Ages, it was just passed on from one generation of scholars to the next without ever really evolving very much. So look, Aristotle was around from 384 to 322 BCE. Okay, and just take a moment to consider just how long ago that actually was. Right, this is somewhere between the Christian Old Testaments and New Testaments being written. And the history of Christianity is all tied up with Aristotle. Christianity is basically Judaism plus Aristotle. because St. Paul showed up in Rome, which was fully Greekized. It was Greek intellectual culture, and Christianity is what occurred when Greek rationality and philosophy hit this very emotional, religious Jewish style thinking. So there's a lot of baggage attached to Aristotle and to the history of logic because of that. So look, it was really Aristotle who first wrote this stuff down. Greek philosophy was usually done by talking and arguing. So probably Aristotle was just writing down things that everyone else was doing anyway. But it's the oldest version of this we have in text. So Aristotle's text begins this process of analyzing arguments and trying to dismantle them into syllogisms, and then he tries to classify what all the valid kinds of syllogisms actually are. So this is the most famous one. Aristotle didn't actually write like this. He didn't write with the lines and the premises and the conclusion. Aristotle just wrote in free-form text, which is really, really hard to read. What you see in this notation is the product of 1,000 years of people thinking about what Aristotle wrote, and they've found a much better way of presenting it and talking about it. And he created these concepts of validity and soundness, right? So an argument can be valid even if the premises are incorrect. Yeah. So this could say Socrates is a cheese. All cheeses are mortal. Therefore, Socrates is mortal. That would be a valid argument, but it isn't sound. It's only sound if you agree with the premises as well. So Aristotle then went through a whole bunch of arguments by other people. So arguing was a competitive sport in ancient Greece, as it is today in Parliament and Oxford. People fight each other with arguments for fun, and there was a wide collection of famous arguments circulating in written forms. And so Aristotle could go through all those arguments and try and figure out what were the basic syllogisms that were used to create an argument. And this is what he came up with, these three groups of syllogism forms. Again, this wasn't his notation. This took 1,000 years to get codified into the easy to read symbols that you see here. And this is a little different from modern logic because Aristotle thinks roughly in terms of what we would call classes rather than objects. So even in the famous syllogism, Aristotle doesn't really have a concept of Socrates as an individual. He really has a concept of the class of Socrates, so that there could potentially be more than one Socrates. What he's really saying is something like the property of manhood belongs to the property of all Socrateses, right? Or the class of Socrates, the class of Socrateses is a subset of the class of men. Again, if you've been conditioned with object-oriented programming, you'll find this quite strange because you're really trained to think in terms of classes and objects, whereas for a long time in logic there was only class. We sometimes get this today, right? You might think, for example, I don't know, Batman is an individual. Batman is one object. But if you read a lot of comic books, you'll find there are cases where there can actually be more than one Batman. There are some comic books where Commissioner Jim Gordon has to take over being Batman for a while, and he wears the costume and he becomes Batman. So sometimes you might think that you're dealing with an individual, and it turns out to be a class. What are other examples? Groot. I think if you got any Marvel fans, for a long time we thought Groot was an individual, but it turns out there's actually loads of them, and he's just the last surviving Groot from a whole planet full of Groot. So look, in this notation then, we're talking about properties and classes as being kind of the same thing, right? So being a Socrates is the same sort of activity as being a man in this notation. So for example, here, look, you can say the capital letters are things and the little letters are relations between them. And the little letters are given these meanings. Belongs to every, belongs to some, does not belong to some. So you can probably find Socrates is a man, all men are mortal. Therefore Socrates is mortal in here. In fact, I'm going to ask you to do that as part of the exercise. Okay, but let's just take a look at some examples, right? Let's look at this first form. So this thing says, it says if property A belongs to all B's and property B belongs to all C's, then property A belongs to all C's. Okay. Now, does that make sense? It's different from notations you might have seen in systems like Prolog.
Isn't the first form, couldn't that be considered Socrates as a man or man mortal? Because you're saying all Socrates are men, and all men are
men. All men are mortal. Yeah, therefore all Socrateses are mortal. Yeah, there you go.
Yeah.
Okay. So it's important to understand the way around this is going then. Yeah, we're saying this property belongs to all the members of this class over here. Yeah. So we have other relations. You can say belongs to no one. So you could say manness, or if you like femaleness, for example. Femaleness does not belong to any Socrates. And what would you say then? Socrates belongs to mortal. Therefore, femaleness belongs to all mortals, maybe? Okay, have a think about it. Then you've got belongs to some. Yeah, this would be a property. Mortalness belongs to some men when you have the I, B-I-C, or does not belong to some. Okay.
So is belongs to some inclusive of belongs to every? Because otherwise does not belong to some wouldn't need to exist.
Well, you could infer it, couldn't you? If you know X belongs to all Y, you can conclude that X belongs to some Y.
Yeah.
That would follow from it.
Cool.
Okay. So look, I'm going to give you an exercise to try doing some of these in a minute. So let's save it for then. In the Middle Ages, this notation evolved, and each form was given a name based on the vowels in it. So this thing is called Barbara because it's got A are the three vowels, and they invented sounds around it to help you remember it. And Festino would be the one with E and I and O and so on. So this logic stuck around for a very long time, right? Over 1,000 years, and logic existed as one of three subjects in the academic system that were known as the trivium. This is still taught in some places today. This is what is meant by a liberal arts education. So there are liberal arts colleges in America based on this. Some of the really old English schools are still very influenced by the. They're also known as a classical education, and you would study grammar and logic and rhetoric. You'd study grammar at school. That's why it's called a grammar school. And then you go to university and study logic and rhetoric. So this is in Oxford, right? This is the School of Logic in Oxford, which exists as a kind of ceremonial building. And I went in there once to do something very, very bizarre indeed. If you if you've studied at Cambridge and you move to Oxford, they don't recognise your degree because they say you need a valid degree from a reputable university to be allowed in as a graduate, and they don't recognise each other's first degree. So you have to go through this very strange and ancient ritual behind that door so that they can make you a member of Oxford without having a first degree. And that was really one of the strangest things I've ever done. Very, very strange indeed, and very secretive. So not much logic actually being taught in the School of Logic anymore.
Hang on. Is that all you're going to give us about the strange thing?
That's all I'm going to give you.
Okay.
Yeah, otherwise he'd be hunted down.
Oh, okay, okay.
If word got out that he told us.
I see. Okay.
There'd be severe consequences with weird things.
Let's just say that there's a reason why Freemasons give out degrees as well, and why they wear mortarboards. Right? The mortarboard is a thing for making buildings with cement, yeah, like a cement mixing person. Yeah, so look, logic used to sit here in the kind of middle year of the curriculum, right? So grammar isn't what they told you it was at school. Grammar does not just mean syntax of language. Yeah, that's a part of it. But the real purpose of grammar is understanding what exists and what is the structure of the world that you want to discuss, and how are you going to use symbols to represent that world. How do you combine those symbols to create meaning? So, what is an object? What is a property? What is a relation? What does it mean for an object to have a property? These kinds of questions. And these are still very relevant questions. Nowadays we call this ontology, and it shows up in subjects like database design and in the foundations of AI. How do you actually represent objects in the world with symbols? So you go and do this at grammar school for a while, and then you'd study logic, and your logic would mean studying those syllogisms, and typically you'd be given an existing argument, and your task is to look at it and decide whether or not it is valid. Yeah, so you're being given arguments, and you're studying them and testing them. And then in the final phase, you do rhetoric, which is how you create an argument. Now you go from studying the other people's arguments to building your own. So, this is still roughly what you get in a university education today, right? Your first year consists of things like computer architecture, where we teach you a bunch of facts about what exists in the world of computer science. What are the basic objects, and how do we represent them and symbolize them? And your second year consists of doing some stuff with those facts, and maybe building some simple systems, or looking at other people's systems and putting them together into structures. And then in the third year, you're supposed to learn to think and argue. And that's why we examine your third year exams as written English questions, and you have a human marking it, whereas your first year exam is marked by a automated in-class test, because we're just testing for the facts. So grammar and logic were bundled together in this big book, and this is called the Organon of Aristotle. Okay, but it's not that big, right? You can buy this for like £10 on Amazon. They got the Organon, and this is all of the Western classical education taught for 1,000 years, all in one book for £10 on Aristotle. And it's full of very dense text, and none of those nice graphical syllogisms or notations at all. And you realize how hard it was to do logic before the notation was invented. So the Organon contains Aristotle's categories is the famous one, and the prior analytics is the logic one. And then you can buy rhetoric for another £10, which is still used today by politicians and Oxford wannabe politicians. It's used in debating to figure out how to make a convincing argument. Rhetoric has quite a bad name nowadays because there's a lot of focus on convincing people to believe things in ways that are not logical, by appealing to people's emotions, or making arguments that are incorrect. These are the arguments that are taken up by the lawyers and the politicians. Well, we're more interested in real logical arguments. So you'll still find some of this in subjects today, right? If you're studying law or politics, or even an MBA business class is inspired by this way of thinking. MBAs are taught to be logical and then to use rhetoric to argue for what they've deduced from the logic. So as we saw in architecture, this held up for a long time until Boole in Lincoln revolutionized it all by fusing it with mathematics. Up till this point, it had been an arts subject, and Boole was this crazy guy who just came from nowhere, from a shoemaker's family, and spent his weekends wandering around in Lincoln Library, and no one told him that some books were supposed to be arts and some were supposed to be science. So he just wandered around from one side of the library to the other and came up with this crazy theory to combine it all together. And so Boole was able to transform these patterns of argumentation into notation and then into mathematics. So you can take a logical argument like this, x and y, or x and z, and transform it. There's an extra bracket that shouldn't be there, and transform it into an arithmetic operation. These are logical truths and falsehoods and logical operations, and these are numbers. These are zeros and ones, and additions and multiplications. And you have to fudge it a little bit because 1 plus 1 has to equal 1. That's the ORing operation. But as long as you're willing to make that fudge, you can then turn your logical problems into mathematics and do them as mathematics. So in this modern notation of sequence, this is roughly what Boole came up with. So Boole's saying, here are two premises. If you know x and you know y, but these are two inputs, you can then deduce x or y. Okay? If you know they're both true, then you're allowed then to say that x or y is true. And similarly, if they're both true, you can say x and y is true. You can go the other way around. So if you're given x and y, you can go and conclude x, or equivalently y. Okay, and then to make it work, you need some extra rules. So these are axioms because they have no input; they follow from nothing. So Boole assumes that x or not x is always the case. So he got this directly from Aristotle again, and it's for a long time it was taken as the very basis of all of logic. Either x or not x must be true, but not both of them. Okay, so it's not the case that x and not x are true. So together these rules are saying x either has to be true or it has to not be true. And this is so obvious that it just hung around for really 2,500 years. It was until Gödel's theorem came along. That was the only time when we realized this isn't quite correct anymore. So talk more about Gödel as we go along. But roughly, Boole is assuming that everything is either true or false. So there's no concept that a statement might be unproven, or that maybe you don't know a statement. You can't express these ideas in Boolean logic. Everything must either be true or false. in Scottish law, there are 3 verdicts. You can be guilty or not guilty, or you can be unproven if there wasn't enough evidence. So you can have a 3rd verdict to express the fact that we just don't know whether you're guilty or not. So you also notice Boole has lost these concepts of any, some, all, and none. Right? These came from Aristotle, but Boole is more concerned just with what we now call Boolean logic, the ands and the ors and the nots. So Frege comes into this a little after Boole. This is 1879. So Frege is the greatest philosopher that you've probably never heard of. Anyone heard of Frege before? Anyone read Frege before? No. Don't all shout at once.
Only the
Heard but
crickets.
not read.
So Frege is your philosopher's philosopher, right? Everything we do in Anglo-American intellectual world now is a direct descendant of Frege, and this created all of what is now called analytic philosophy, which is different from what they do in Europe. So Frege made, like all these people, he was a logician. He didn't make any distinction between logic and mathematics and philosophy. They were all a single subject called logic. But Frege effectively took Boolean logic and put Aristotle's all and some stuff back into it. So these symbols were introduced later by Gentzen, but effectively Frege introduced this notion of allness and existence. So now you can go back to saying all men are mortal, or some cats are black, all that kind of stuff. And in modern notation, we can define them using these rules. Now this symbol means text substitution. Okay, phi with t substituted for x means you are going to take whatever was in phi. So phi might be the string hello x. And if you do this notation, this means you're going to substitute the word world for the word x, and you end up with hello world. Okay, so roughly then this means if you know that for all x something is true, so for example, for all men they are mortal, you can take that thing and you substitute a particular person like Socrates for all the men, and you'll end up with Socrates is mortal. And similarly, but the other way around, if you know that something is true for anyone you care to substitute, you can then conclude that at least someone has that property. So if you know that Socrates is mortal, so this is all men are mortal with Socrates in there, you can then go and conclude that some men are mortal. So Frege's original notation was completely crazy. Not going to show it here, but it looked somewhat like actual instantiated digital logic. It was graphical, and you could almost have imagined him going on to invent logic gates and logic circuits coming from that. But he was a little too early. So we don't use Frege's notation anymore. We use this sequent notation with the things above the line and below the line. And we use these upside down A's to mean for all, and we use a backwards E to mean for some. Right. Shall we have a break and do something a little more practical? Are you ready to?
Yeah, definitely.
Stop listening and start doing for a bit.
Sounds good.
Yeah.
Yep.
Okay. So look, I've done a little Aristotle challenge for you all. I don't know what's wrong with Blackboard today. Normally you can click on the slide number you want to go to, but it's making me click through the slide out of time. So I've created these little breakout groups on Blackboard. So we're going to have to put people into small clusters somewhere, and then we'll get you to go and sit in those breakout rooms. And let's try and do these. Okay, so I've got three tasks for you, right? So task one is take a look at those syllogisms. There's the slide with all the different syllogisms on, and try and create one example for each one of them and check that it makes sense. Okay. Then we've got try and find a English language argument of your choice, maybe something political if you like, and try and map it out using that notation. So, especially if it's something controversial, can you map it out and then discuss where any problems in the argument might lie or where any disagreements might occur? So is it valid? Is it sound? And then if you get through all of that, Aristotle's logic is not perfect. There is a bug in Aristotle's logic, and it sat there for almost 2,500 years, I think, before anyone noticed. So see if you can find the bug, given that we now know it's there and that there are some clues over there. Okay. So how shall we put you into groups? So we've got 13 people sitting in here. So we have, and I know a couple of you don't have your mic working and stuff. It's going to be tricky. Shall we put you into 3 groups of 4 then?
Sounds good.
One group with 5. If you want to just self-sort into those groups, just pick a random number between 1 and 3 and log into one of those groups. And if there's too many people in it, then go and pick another one. Right? So logistically, you can stay in this room as well, I think. In particular, we can all be on the text chat.
You can. I'm in a group at the moment.
Which means that when we come back, I can put the thing in the text chat saying, please can we all come back to the main room. And while you're trying to answer these questions, I'll come around and sit at your virtual tables and listen to you for a while, as we would do in a classroom. Yeah?
Good.
And feel free to work as a team, or if you want to have some people doing different syllogisms or doing different parts of the task, whatever, then go for it. And I guess, how long should we give this? Let's come back in half an hour, say, for 45. We'll come back here and see how everyone got on. Yeah. So any questions? Does that all make sense?
No.
Right. So yeah, let's get everyone jumping in those rooms, and I'll see you in those rooms. Then I'll see you back here at 4:45. Okay, hello. Is everyone back in the main room? Is everyone back in the main room?
Hello.
I'm here.
Hello. Hey.
Yeah.
Hello.
So, shall we just take a quick report from each of the groups and see how we got on? Does anyone from Group 1 want to tell us what you've been doing? Just for 2 minutes.
Yeah, so we have spent the whole time talking about the third problem because that was really interesting. We were looking at lots of different ways of applying the output of this to other things, and I'm not sure that there's any like particular bug in the logic if you assume that all of the classes and the axioms are true. But let's say if you have something like unicorns pink and fluffy here. When I say that all unicorns are pink and all unicorns are fluffy, there's the implicit statement that there is such a thing as a unicorn.